Last week we used these 5 people and we were describing how many ways we could put them in order. So we said if we needed to put these 5 people into a group of 3, how many different ways can I arrange those groups of 3 or a group of 5? But now what we're going to do is we're going to take away the idea of order mattering. So let's say that I wanted to take these 5 people and I wanted to put them in a car that only had 3 spots available in it. I'm not going to number these spots because it doesn't matter what order they're in. So when I say order doesn't matter, what I mean is, for example, let's say Abby, Ben, and Carl are one of the possibilities. Well, when we were talking about permutations, another one of the possibilities was Abby, Carl, and Ben. Now that we're talking about combinations, that's not going to count because that's still the same 3 people. So when I say how many permutations are there, I'm asking how many different ways can we arrange 3 people? And all of the different orders matter there. If I'm saying how many groups of 3 can we put into this car, I'm saying how many combinations are there? Or in other words, how many groups of 3 can we put in here that are unique groups of 3 with order not mattering at all? So ABC counts, but ACB doesn't, BAC doesn't count, BCA doesn't count, CAB doesn't count, and CBA doesn't count. So there are 6 possibilities there that we're sort of boiling down to just the one. That's the only one that would count there. And that's an idea that's going to matter here. So we can still take this same concept of multiplying our terms, but we're going to have to do something in the end. So I'm going to say that there are still 5 people who could take that first spot. There are still 4 people who could take that second spot, and there are still 3 people who could take that third spot. But since order doesn't matter, I want to make sure that for every one of these combinations, I remove all of the other ones that are the same, or the same 3 people. So let's take that formula that we came up with permutations and change it a little bit. So in this case, I'm going to say that I have a group of n and I'm choosing k people. So remember, k has to be less than or equal to n, and order does not matter. The way that we're going to write this is we're going to say that this can be rewritten as nk in this format, which means n choose k. So we're choosing k people from this group of n, or choose k elements from this group of n elements. And if I want to calculate this, I can still do what I have been doing, and I can still do n factorial, and I can still divide that by n minus k factorial, just like we did in the last example. But now we have to be careful and add one more component to this. Because remember, in the past with permutations, these 6 all counted. And that's because when I'm talking about putting 3 things in a group, there are 6 different ways to put 3 things in a group. But now those 6 different ways don't matter. I'm only going to count one of the 6. So I have to divide this by 6 because I don't want to count all 6 of those for all of these different permutations of groups of people that we could put here. So I'm also going to divide this by k factorial. So when we're talking about a combination, this is the formula we're going to use, and I'm just going to use it here, and we can hopefully walk through this logically. So in this situation, that means that I'm going to choose 5 factorial to be my numerator, because I'm still picking from a group of 5. But because I don't want to count in that 5 factorial the 2 and the 1, I don't want to count those, I have to divide this by 2 times 1. And the way that I'm going to do that is by using that permutation formula that we used last week. So I'm going to divide this by 2 factorial. And that's going to get rid of that 2 times 1. But I also need to get rid of the overcounting that I'm doing. See, I'm taking still, in this case, I'm taking ABC, and in this group, I'm also counting ACB and BAC and BCA. I'm counting all these possibilities still. So to avoid that, I'm going to also divide this number by the number of different ways to arrange 3 things. And we know that the number of different ways to arrange 3 things is just 3 factorial. So this is that formula at work. This is 5 people, choose 3 of them, order does not matter. So there's my 5, that's the 5 people, the n choose k, or n minus k factorial is 2, because 5 minus 3 is 2 factorial. And k factorial is the 3 that I was choosing, and so this gives me my final result. So back to my illustration up here of what's getting done. Now I'm also multiplying this by 3 times 2, and so you're going to see that those 3's cancel, and in fact this 4 reduces to a 2. So the end result here is that there are 10 ways to do this. Or in other words, there are 10 groups of 3 that you could pick to put into that car. Let's do one more example. So Corey is packing for his vacation, and he can only fit 4 t-shirts into his suitcase. So it's good to sort of visualize the 4 spots that are available. But there are 9 t-shirts to choose from. How many different groups of 4 t-shirts can he take? So he's got a bunch of t-shirts. 3, 4, 5, 6, 7, 8, 9. 9 of them. And we're putting these 9 t-shirts into a group of 4. So how many different groups can he take? And we have to sort of determine, is this a combination situation or is this a permutation situation? So think about, does this matter? So these t-shirts are all maybe different. Maybe this is a yellow t-shirt, and this is a blue t-shirt, and we've got a red one, and a green one, etc., right? So a lot of different types of t-shirts that he might have. One's ripped, one's long sleeve, whatever. Is the combination of yellow, blue, red, green, if those go into the suitcase, is that any different than if it's blue, yellow, green, red? And the answer is no. I don't want to say that these are 2 different things. The question is, how many different groups of t-shirts can he take? Not in order at all. It doesn't matter what order you put the t-shirts into the suitcase. This group of t-shirts is the exact same thing as this group of t-shirts, because at the end of the day, it's still just these same 4 t-shirts. So this is a situation where we want to deal with a combination, not a permutation, because if we deal with a permutation, now what we're going to be doing is counting each individual case like these, and we know that there are tons of those. So what we're going to do is get out our combination formula here and say that what we're doing is, from a group of 9, we are choosing 4 elements, and we know how to handle this. We're going to have 9 factorial be our numerator, because there are 9 possibilities for the first t-shirt that's chosen, 8 possibilities for the second, then 7, then 6 possibilities after that. But remember, I don't want to include the 5 times 4 times 3 times 2 times 1 that comes from this 9 factorial. So I'm going to divide this by 5 factorial to get rid of those. And remember, by our formula, which says that n choose k is equal to n factorial divided by n minus k factorial, that's what that 5 factorial is. But don't forget that the other thing we have to account for is that even with this, we are still counting each of these as a unique and different combination. And we aren't going to try to do that here. So the question we need to ask ourselves is, how many of these are there? So for this yellow, blue, green, red situation, how many of these different variations of these 4 t-shirts are there? How many different ways can I put these 4 t-shirts into a different order? And that's a permutation question. How many ways are there to put 4 things in an order? There are 4 factorial ways. So I'm going to put the 4 factorial down here because I'm also trying to eliminate those possibilities. So what I end up with here is 126 different combinations or different groups of 4 t-shirts that he could take. And another way to visualize this, remember, is you could see this as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 divided by, and then we've got our 5 times 4 times 3 times 2 times 1. That's that 5 factorial times 4 times 3 times 2 times 1, and that's the 4 factorial. And so you can visualize a lot of things canceling here. You can see that those would cancel. There would be a 3 there that would cancel, and a 4 there that would cancel. The 5 that would come after that would cancel. The 3 and the 2 here would cancel with the 6 that would have been there, right? 8 and 4, that's a 2 and a 1. And so you're just left with 9 times 2 times 7, which is 126.